Number one, what are we? Sino ba tayo? Number two, where did we come from? Saan tayo galing? Number three, where are we going? Saan tayo papunta? And you must be asking these questions yourselves. For yourself, for example, saan ako galing? Saan ako papunta? But today I'm going to share with you answers to these questions for the universe as a whole, for the galaxies. What are we? What is our place in the universe? Where did it come from? Where do galaxies come from? And where are we going? Where is the Milky Way going? And so let's start with what are we? What is our place in the universe? And this is a film of the known universe. Everything here is based on scientific data, astronomical measurements. And you start from the Earth and zoom out to the farthest reaches of space. So we start from the surface of the Earth. And from the surface of the Earth, it looks flat. So for a long time, people thought that the Earth was flat, right? But as we zoom out, you start to see the horizon. You start to see that the surface of the Earth is curved. And as you zoom out even further, it starts to become apparent that we are actually living in a sphere, in a ball of water and land. This is our planet, we call Earth. We live here in the Philippines, covered with clouds, probably storms going on. And this is our planet. Now you start to see the orbits of the artificial satellites that we have sent out into space and go around the Earth. This is how our GPS works. This is how we actually image the Earth. We image our farms, our lands, the waters. And we also send out telescopes into space to look at the galaxies. Now we start to see the sun, our star. Our star, we go around it once a year. And as you keep zooming out, we start to see the orbit of the moon. Natural satellite that goes around us once every month or so. And now you start to see the moon's orbit shrinking, and you start to see the orbits of the other planets. Mercury, Venus, closer to the sun. Farther out, Mars. And then farther out, the gas giants, Jupiter, Saturn. And this is our solar system. You start to see the stars from our point of view, constellations. And as we move out light years away from the Earth, our sun starts to look just like the other stars. It's a very average star in the Milky Way. And so now you can even differentiate it from the other stars. This is how far radio signals have reached. Now you start to see the center of the Milky Way. We're in a spiral arm, about 2/3 of the way from the center. This is, of course, an artist's impression. We cannot take a picture of the Milky Way, but this is how it looks like. It's a galaxy. As you zoom out now, you start to see other galaxies. So the green dot is here. Each green dot is another galaxy. Hundreds of billions of stars. And you have now millions of galaxies in the sky. The Sloan Digital Sky Survey. And further out. And these empty areas are just places we haven't looked. But of course they also fill with galaxies. There's a structure here. Galaxies are clumped together, and there are places with not a lot of galaxies. This has been called the cosmic web, and I'll talk more about that later. But as we zoom out to the furthest light that we can see, cosmic microwave background, just 400,000 years after the Big Bang, which was 14 billion years ago. And that's how big the observable universe is. And now we zoom back in, flying through the universe, flying the galaxies, back to where we are. There are many different types of galaxies, which I'll show you later. But we are living in this one, spiral disk galaxy, beautiful one, made of hundreds of billions of stars. And now we have detected thousands of planets orbiting around these stars. The recent estimation show that typically every star would have at least one planet going around it, just like the Earth is going around the Sun. And so the galaxy is filled with stars, which is also filled with planets. And you just zoom back into this particular one because this is really good. We have a bias. So now when you see the solar system, now you feel close to them. This vast universe, they are our nearest neighbors. Third rock from the Sun, the Earth. Only now the Moon's orbit becomes apparent. And you have the pale blue dot. Everyone who's ever lived, everyone you know, 7 billion people live in this planet, our Earth. So welcome back home. Next slide, please. So this is our answer. We have answered this question: what is our place in the universe? Where are we? We are on a planet called Earth, which is just one of 8, going around the star, the Sun, which is just one, 100 billion stars in the galaxy in the Milky Way, which is just one, 100 billion galaxies in the universe. So this is our place in the cosmos. We feel very small. It's vast cosmos. But at the same time, we're also very powerful because we can see out, and we actually live in the generation that has mapped out the universe to the farthest reaches. So next slide. So we'll use that as a context for answering the next 2 questions. So where did we come from? Where do galaxies come from? There wasn't galaxies in the beginning. We'll start from the beginning. Next slide, please. This is the cosmic microwave background. This is the sphere that you saw from the animation, from the film. And this is microwave radiation that bathes the universe, that we measure from all directions. This is a map that shows you the temperature in all directions in space that we measure it. And what this tells you is that some places are slightly cooler, the blue ones, and some places are slightly hotter, red ones. But the differences between these cold and hot spots is very small. It's just 1 part in 100,000. So it's 1.00001. So essentially everywhere you look it's the same. So the universe in the beginning was very, very smooth. There were no galaxies, no stars, no planets, no people. So I want to explain how we got from a universe that was very smooth 14 billion years ago to a universe today which is filled with galaxies. And that's what we see today. Universe filled with galaxies. This is an image from the Hubble Space Telescope. So it's a telescope in space. It looked out the patch in the sky. It's very dark. When you just look at it by your naked eye, you don't see anything there. But it waited months to capture the light. And this is what we see. It's filled with galaxies. So each blob here is a galaxy, except this one, this is a star with diffraction spikes. Most of the other blobs, galaxies, are made up of hundreds, billions of stars. This one is a spiral galaxy that looks just like the Milky Way. This one is also a spiral galaxy, but it's edge-on, so we see it this way. So it's like a plate. You can see it depending on how it's oriented towards you. You can see it either face on or edge-on. And then there are galaxies that are spherical, like this one. And we know more. We actually have mapped these galaxies where they are. And this is from the Sloan Digital Sky Survey. Also saw this in the film, where each point here is a galaxy. And this is the Earth, and this is the distance of the galaxy to us, and its position in space. And you see the cosmic web. There are filaments, there are places where galaxies are clumped together, and then there are dark places, there are voids where there are no galaxies at all. And we want to explain this, and in fact, we could explain this. And I'll show you how. So the basic picture is timeline, start, Big Bang, 14 billion years ago. Over time, stars form, galaxies form. The universe evolved to what we see today, filled with galaxies. Yep. So how do you build a galaxy? We'll do it in 2 steps. Step 1, build the universe. Build the universe with galaxies. Now, to build something, you need to know what it's made of. For example, you're going to make adobo or cake, you need to know what ingredients to put in. What flour, right? How many eggs, or water. And so, we have to know what the universe is made of. And in fact, we do know what it's made of. Next slide. This is a pie chart of what the universe is made of. And what you notice is the atoms, everything you know, everything that makes us up, everything you see, stars, galaxies, everything you learn in chemistry, periodic table of elements. It's a tiny portion of the universe. It's 4% of the universe. We're not even the dominant stuff in the universe. As the dominant stuff in the universe, it's something that doesn't emit light. We call it the dark matter. Dark matter is 23%, about 5 times more than the atoms. And we know that it's there, we can detect it because we can measure its gravitational force on the objects that we see. But we haven't detected it directly. We think that it's an elementary particle, doesn't emit light, doesn't interact very much with matter. And there are experiments that currently are ongoing trying to detect this dark matter particle. And then there's a big chunk, almost 3/4 of the energy content of the universe is something we don't really quite understand yet. The simplest picture is that it's dark energy. Like dark energy is the energy of space, the energy of vacuum. And what it does is that it makes the expansion of the universe speed up, makes it accelerate. So 1997, astronomical observations, with astronomical observations they found that the universe was in fact, the expansion is actually speeding up, not slowing down. And it was a surprise, and it eventually won the Nobel Prize last year. But the simplest explanation is that this is the energy of a vacuum, which is repulsive and makes the universe expansion speed up. And we're still trying to understand what it really is. But this picture, this is a standard picture of cosmology. It explains everything we observe. It explains cosmic microwave background, it explains structure of galaxies. So we can start here. The dark matter, which dominates the mass, and we put it in a computer. Right? And this is how it looks like. Every galaxy you see, including our own, is actually surrounded by a large dark matter halo that has 10 to 100 times more mass than the galaxy itself. So every galaxy has this halo, or you can say that galaxies live in centers of dark matter halos. So to understand the evolution of the universe, you can start with just the dark matter. And then you turn on gravity. Step 2, turn on gravity. Why gravity? Because gravity is the force that governs the larger scales of the universe. It's always attractive, and so over time, gravity makes matter come together, and that's what we see. So I'll show you a film. I'll show you a film, a simulation of the universe simulated in the computer. So we start very early in the universe. It's still very smooth, and over time, gravity clumps matter together into concentrations. Until the present day, where you actually get the structure, places where there's very dense dark matter concentrations, and that's where galaxies live. Galaxies live in the centers of dark matter concentrations. So there will be lots of galaxies here, in these filaments, and then there are these voids. And this looks like what you see, the map of galaxies that I showed you earlier. Do you want to see that again? Let's do it one more time. So we start very early, and you see in the beginning there's very small differences, and that's from the cosmic microwave background. If you remember, there are places where it's slightly hot, slightly cold. So it's there, but what happens over time is that the rich get richer, the poor get poorer. The places where it was initially more dense become even more dense because it casts the matter around it. While the places that was initially a bit less dense get even more dense because the matter around it is taken away by the richer places. So it's not very equitable, but it's beautiful. You have this structure, and that's what we see today. So the basic picture is, you start with a very smooth universe, over time gravity acts, and you end up with a very clumpy universe with the cosmic web that we see today, and galaxies live in places where there are more matter. And then you have the third step. Step 3, you have to add the atoms, you have to add stars, things that you see. And this is the hard part, because then you have to take into account more physical laws to put in. But we're starting to do it, and I'll show you a state-of-the-art simulation that actually it has gas and can form a galaxy like the Milky Way today. Right? So it starts very early in the universe, and what you'll see is the actual gas densities. So less than 1 million years after the Big Bang, we have first small galaxies, and then they merge together, and over time, matter keeps falling in to build a galaxy like the Milky Way today. Right, so you see these clumps come together, gravity. It's more messy, not like the earlier simulation, because there's hydrodynamics, there's pressure, there's cooling, there's heating, and then there's star formation. At this point, about 10 billion years ago, we have the last major merger of galaxies, and then you start to see a disk that looks like the Milky Way. So over time, smaller clumps come together, and as we speak, gas keeps falling into the Milky Way, and smaller galaxies, dwarf galaxies that are around us are being devoured by the Milky Way. But I'll tell you, to be honest, what you see here is not exact physics, in the sense that the computers are not yet powerful enough to put in, to calculate exactly all the scales. So for example, star formation, here we just use a recipe for star formation. For example, if you have a box that has more than this, then you make stars. So don't actually have the power yet to simulate it in all scales, from the stars to big galaxies. But this is the state of the art. You have recipes, and then you try to understand, try to improve your recipes, try to improve your understanding of the physics of galaxy formation. It's a very open field. This is what I'm working on right now, more on the observational side. There's a lot to learn. So my work is using observations to test these kinds of simulations, for example, if they really match what we observe in the galaxies. So that short film took 8 months to do in a supercomputer, and that's state of the art. But in the future, we hope to do suits of galaxies in your personal computer. It will take 600 years, just to give you a flavor of the computation. That's where we are. This is state of the art. This is from just a year ago, and we're trying to build on that and keep understanding. Maybe some of you would help in this field. So now I'll talk a bit about where we are going, where the Milky Way is going in the next 3 billion years. I'll show you a picture of, next slide please, a beautiful picture of the Andromeda Galaxy, which is the newest big galaxy close to us. It's 300 million light years away. And this galaxy we measured is actually moving towards us. So next slide. Show you a picture of two beautiful disk galaxies, parallel galaxies merging with one another. And so this is your flavor of the future of the Milky Way and Andromeda. In 3 billion years, we will collide and merge into one big galaxy. And I'll show you a film that shows how that will look like. Please. So you have two disk galaxies, one the Milky Way and Andromeda. They are attracting each other, gravity. And 3 billion years from now, they will collide